So good morning. We're going to continue on some of the same algebraic topics we did last day. Now, we are at the halfway point, so I just want to give some gentle reminders to people, mainly keep it up. I know that the burnout is inevitable because of the pace we're going. My fear is that people don't do more as the semester goes on. They do less and less and less. That the quiz is the only attempt we ever make at particular types of problems, which is extremely dangerous. Because I've said it before and I'll reiterate, I actually do have an expectation that every single student is attempting every single problem, or at least can do every problem in the text. And I get, people don't realize it. Not only do I actually do every quiz problem in detail before I ask you the question, which does make it a little easier to get the answer, you have take-home quizzes that are open book and untimed. It is actually expected that people turn in perfect quizzes, and the majority of quizzes are perfect or near perfect. You know, there are the occasional typos, but the expectation is, no, you should be turning in perfect quizzes. And so I get the constant emails every day of saying, why are you taking points off my quiz? And my reaction is, why are you turning in flawed quizzes? Why in the world would you turn in and say Euclidean algorithm problems that are incorrect? Why would you do a proof by induction where you actually disproved what it was you're trying to prove and then turn that in? No, make them perfect. Now, what's interesting, I've noticed, the quizzes that are turned in first each day, the first 5 to 10 quizzes are almost always perfect scores. The last 5 to 10 quizzes are usually the ones with the most deductions. I wonder why that is. The ones that are turned in at 758 and 759 tend to have more errors because it looks like they were, rushed at the last minute. You don't want to do that to yourself. So use the weekend to put yourself ahead of the pace, not behind the pace. Now, in terms of content, okay, just want to make sure we're on the right page. Today is lecture number 6 of the 8 lectures that are on exam 2. We have lectures on Monday and Tuesday, and then the exams at the end of the week. I will be posting a practice test over the weekend because I know a lot of you like to get that head start, and it is wise. Chapter 8, which is the Monday, Tuesday content, is not terribly rigorous. I mean, yeah, it's still abstract and proof oriented, but it's not calculation based, and there's not a lot of parts on there that people will tend to struggle with. In fact, a lot of it will feel like stuff that we've dealt with before. We're just going to take it a little bit further. So again, I do encourage you, take the time and effort to turn in excellent work. And it's interesting, every time I hear complaints about why'd you take points off, I just laugh. You do have to understand, if 1 point is taken off, then it's actually justifiable to give a 0 on the problem because it means it's a flawed answer. Answers are perfect or they are not. Not perfect. Everybody I've ever worked with in my life, if it's not perfect, they just give a 0. They don't bother looking for things that are right. They don't bother with partial credit. There actually is no such thing as partial credit on a proof. There's no such thing as partial credit on a Euclidean algorithm problem that goes astray. I tend to give partial credit because I'm looking for what you did right, but things on a quiz should be right. Now, exams are a different story. I say perfection is your goal, but no one really reaches it very often. But quizzes, yeah, perfection is an expectation because you can. There is no reason in the world anybody should ever turn in a quiz that's not perfect. It's short, 15 minutes usually is about the max. So it's not about the grade. It's not about stockpiling points. It's about making sure that you have certainty in your technique. We've talked about this before. Uncertainty, doubt, that's the one thing none of us can afford. We want to be certain that what we did is actually correct. Now, today we're going to continue on proofs, but now we're going to do it from a very different point of view. Last day we did element proofs. So we were starting with a statement of 2 different sets. It might be, A union B, and over here I might have the complement of A intersect B or something. And I was showing one set was contained in the other, or 2 sets were actually equal. So we had containment both ways. That's called an element proof. Today, we're going to do more like the logical equivalence stuff that we did with statements. In other words, we're going to say a statement is true by the following. And so I want to walk you through the process because the process should feel very familiar. It should feel a lot like the P and Q logical argument stuff. So I wrote down a couple problems that I want to do today. So the first one, it's basically the instruction is simplify this. Now, it's not simplified yet because I have operations going on. Now, one question that is often asked is, okay, we did the set difference thing. We showed this yesterday, and this is actually a really, really important, it's borderline formula, identity. I don't care which way you call it. It's really, really important. If I got down to either one of these statements, the question is which one is considered more simplified than the other, because that is a little bit ambiguous. In an algebra class, if I have a square root in the denominator, I'm not always sure if that's simplified or not. In this case here, we considered this one simpler because it doesn't have a complement. An answer that has a complement in it is usually not considered as simplified as one without the complement. So if I get down to either one of these, this is the one we would finish. So if this was your last statement, you wouldn't convert it to this, but if this was your last statement, you would convert it to this. It's not about right and wrong. It's about what do we consider the sort of the simplest version of the answer. So right now I'm giving you something with a difference, but I can't do the union while I have a difference. So it's kind of like, again, in algebra, if I have a root or something in a denominator, we often change it to a negative exponent so that I can do the algebraic manipulation, even though we would consider a negative exponent not a final answer. It's what I need to manipulate. So I need to make this into the other version of the set difference. So my first step, I'll write it over here. This is, and the correct is the equivalence symbol. It's equivalent to A union, B intersect A complement. And now is where we give the reasons. Anybody want to tell me the reason for this? Because they all have names. I want you to be comfortable with them. And a lot of them sound familiar. You may want to try this one. That's the one I had just a moment ago. It's the something law. If you have your book in front of you. All right, I'll help you. It's called the set difference law. No, it is definitely not the complement law. That's something completely different. But we will use a complement law in a moment. This is called the set difference law. Now, I want the parentheses gone in such a way, I want to be able to combine these guys. So this is equivalent to A union B intersect A union A complement. Now, what did I just use there? What, and they're actually called laws. The laws are theorems if you want, but they're like formulas. What did we do there? Anybody?
Distribution.
That's distributive.
I always do that. Yeah, distributive.
Yeah, it's close enough. Distilled, I don't know,
yeah.
Disturbing, something
Yes.
with a dist in it. Have that.
Yeah, exactly.
Distributive law. By the way, I taught remedial algebra for years, and I would give an algebraic statement and I'd say, what property are we demonstrating? And the answers would be things like the associative, commutative law, the distributive, it'd be things like that. Well, I realized early on, I should not have people fill it in. I should just give them the choices A, B, C, D, because I rarely got the word commutative. Most of the time I would get communicative, which is actually not a word. And occasionally, no joke, I get communicative. That's the contagious law, I guess. But my favorite one was I would get things like the dissociative law. Doesn't that sound mathematical? The dissociative law, there is no such thing. It's somebody got confused, distributive and associative, but I would get words that weren't actually words. So A is commutative, B is dissociative, and then you fill in A, B, or C. It was safer that way. But when I had people write the words, it was funny how often I got things that weren't actually words. And even in this class, I still get communicative more than I get commutative. So
that sounds like me.
It's kind of funny. Now, look at this. This guy's fine. You see anything here? I have A and I have A complement.
That's equal to the universe, right?
Yeah. Well, by the way, what are my only choices? What are my only possibilities if I see A and A complement at the same time in a statement? It's either what or what?
The universe or the empty set.
And how do I know union versus intersection? Oh, I have something union with this complement, and you're absolutely correct. That's everything. So that's the universe. And I make the effort to make it look like make it look like a U as opposed to a union symbol, because a lot of times our symbols aren't really clear. Now, what law did I use? I have something with its complement. This is the complement law. Okay. When I have something union or intersect that's complement and get a result, that's what we generally think of as the complement law. Now, I've got this set here, and I want to know, where does this intersect with the universe?
Whoever that.
I think now you have identity law.
No. What's first of all, what's the answer? What's the intersection of this stuff with the universe?
The stuff.
The stuff.
right?
A union
Now,
B.
do I need the parentheses anymore?
No.
No. So it's the stuff, and that is, I heard somebody say it. That's which law?
Identity.
Identity law. Now, does this feel familiar? When we did, P and Q, not P and Q, we did all the things with statements, P and Qs. Didn't we get answers like distributive, complement, identity? Didn't we get those as reasons? Yeah. So this should have a similar feel. So why is this different again? Just the bottom line, the reason this is different is those were statements. I went to the grocery store, I drove a car today. That's not a set. That's not something that can be calculated, that has no value. Oh, but two statements can both happen. I can have two statements, one or the other. I can have the negation of a statement. So those were statements. They didn't have numerical values, and there was nothing mathy about them. We were just doing pure logic. Okay, when I give you a statement, I could ask for the contrapositive and the negation and so on. Okay, great. Now we're talking about collections of things. A and B are sets. Now, it doesn't matter whether they're finite sets or infinite sets. That doesn't change anything. So I think it's a lot safer if you're trying to convince yourself, you're trying to convince yourself of this truth. I like the Venn diagram. You've probably gathered that by now. I think it's just such an easy illustration. I use that in statistics. I use that in linear algebra. The Venn diagram is such an easy visual, but the other way of thinking about it is when you're trying to convince yourself and you can't remember, God, is it this? Is it that? Is it the union? Is it the complement? Think of finite sets. So if you want to give yourself a little example, okay, let me make a set 1, 2, 3. Let me make another set over here. Always make them small and finite to manipulate. Don't think of the sets as being infinite, because then it's harder to come up with examples or even counter examples. So this would be an example. I'm simplifying this quantity I'm saying is equal to this quantity. Now it's a very interesting statement. So what does it look like pictorially? And I say this, if you're in my calculus classes, I tell you all the time, you can never prove anything with a graph. You can never answer any question by drawing the graph. So at the end of every calculus problem, I usually draw the graph. In other words, after we do the calculus problem and come up with our answer, I then draw the graph to say, this is what you just said. The graph isn't the answer. The graph sometimes helps us interpret the answer better. Just sometimes makes it simpler. I never need people to draw a picture, but sometimes the picture is entirely useful. So I've got A and B. Okay, which part is B minus A, by the way?
The half moon of B.
Complement of B? No, I just want this. In my picture, it's all of B.
Like you need to cut that piece. Yeah.
Without the intersection. I'm going to say, don't look at the rest of this. I'm just looking at the opening statement. Do you agree this is B minus A? Everybody cool with that? That's B minus A. Now, A is this. A is clearly this. The orange is clearly B minus A, and now I want the union of these two. Oh, doesn't that make perfect sense? The union of these two is A union B. Okay, I got back my intersection. Now, if I had tried to do this ahead of time, that might have worked. But the problem with trying to do this from a picture standpoint is I might have a third set. I might have a C in the problem. And pictorially, that might be a little bit more intense to try to figure out working backwards by reading my intersections. So let's do another one along these lines. I want this to feel simple. I do not want this to feel complicated. Now, some of the rules, the laws, are a little more obscure and abstract than others, our idempotence and our universal bounds and things like that. So that's why you want to have your book open to the page that has all of the rules, because things like commutativity, associativity, distributive, even Demorgans, you guys probably know those inside and out. It's the more obscure ones that we tend to have trouble with. We know a statement is true. That's not really the issue. It's the why in some cases. So let's do the next one. Next one is A minus B. So if this was an algebra class, what would I write? If this was an algebra class, what would I write with the statement?
Then it would just be
If this was algebra, wouldn't this just be B?
plus 8.
I distribute the negative sign and all that. This isn't algebra. And the answer is not B. But there's a tendency, even discrete math folks can sometimes be deceived. These are sets. So there's no adding, subtracting, multiplying, dividing, exponents, roots. There's no algebraic things. This is not the answer because I can't distribute a negative. Nope. So now I think we agree I'm going to have to use the set difference law. But the question is, do I use it here or do I use it in here? I'm going to write down two things. One of them is correct and one of them is not. And to me, it's not entirely obvious. So I need to make it obvious. If I use this guy, then it's A intersect the complement of that, or it's A minus A intersect. Okay, does everybody understand what I just did? I used the set difference law. So to subtract something is to take the union of its complement. Which of these things do you think is correct? And it really has to do with what I would do next.
Be the left side.
Okay, so then how would you take the complement of A minus B? You can't. So in other words, it's the right. You can't take the complement of a difference. There's no mathematical process for this guy. Oh, so I actually have to do this guy. Now I'm going to have to do it a second time. So this is one of the trickier statements. And I have people will find themselves in this position and then they get stuck and they say, I don't know what to do. I'm taking the complement of a difference. Whoops, wrong erase. Sorry. So I'm writing this down because it's not obvious. I wouldn't expect anybody to say, oh yeah, it's clearly that guy. You know, no, it's going to be this guy. Actually, I'm going to write it. Sorry, I'm going to write it to the left because that way I can fit the reasons in. So this is equivalent to A minus, we'll deal with this one first, A intersect B complement. And the formal way most of the time is we say by the set difference law. If you just wrote set difference or set difference law, you're fine. I like to see the law in there because that's actually the name of the theorem. It's called the set difference law. You know, you don't want to break the law. Now, what do? Now I do it again. Now this is a little bit trickier. So ignore what's here. I have A minus thing. That means it should be A intersect what? What am I intersecting?
Parentheses. A intersect complement of B.
So thing.
And complement over parent.
Good.
Yes.
Now you see what, oh, that just got really tricky. So I like to use formal mathematical vocabulary all the time. I have A minus thing. So it's A intersect the complement of thing. That's absolutely a correct interpretation. And once again, it's by the set difference law. This is one of those rare times you're going to use the same rule twice. Now, I cannot do any form of distributing with that big C sitting there. So what am I going to have to do?
But you can use Demorgans law here, right?
Exactly. Now, Demorgans law says that the complement of an intersection is the union of the individual complements. Now, there's two ways to approach this. I have my own preference, and some people do it differently. What goes here? I have two choices.
B.
It's either B or it's B complement complement.
B complement.
This is algebraically correct, but then now I have to take another step to say B. I find that entirely redundant. And the reason is this is binary. The negation of on is off. The negation of on is never not on. We don't do that mathematically, as in ever. So a double negative, unless the situation dictates it, it's almost never correct to write a double negative. Now, I know in the textbook, the author says at this point, you can use the double negative. What's the complement of a complement? The thing, period. That's an absolute, there is no exception. The complement of a complement is the original thing. So I find this entirely a waste of time. So you're not going to see me doing this and then taking an extra step. No. The complement of the complement is the thing. The negation of the negation puts me back to where I was. The negation of the negation of P is P, because it's binary. So I would prefer to do this. What is the reason? I think Sergey said it. Probably the most important and the most used of all of them. Which one's this one?
Demorgan.
Demorgans. By Demorgans law. Beautiful. Now, if I'm not careful, and this is where some people get in trouble, they're not careful and they've got the wrong symbol here. Ooh, that's life and death. Or here, I have an intersection into a union. Now, I don't know if I should keep going or not, but I know if I combine these, I'm going to have an A and an A complement in the same statement. And that's a good thing, because we said a few minutes ago, when you have A and A complement together, it's either the universe or it's the empty set. And I like both of those because universes and empty sets are really, really easy to combine with other things, aren't they? There's not a whole lot of mystery there. So this is going to be A intersect A complement union A intersect B. And by the way, the parentheses are absolutely critical. You've got to be careful with parentheses. It's kind of like an order of operations thing. Okay. It's not I'm unioning A and then taking that result and then intersecting B. No. That's not how it works. You've got to keep the parentheses where they live. Now, I think we know this one because we just did it, but in case we forgot, what's the reason for this?
Distributive.
By the distributive law. I'm going to abbreviate so I don't have to use two lines here. Now, look at the left side. A intersect A complement.
That's the empty set.
That is the empty set. There's not much to do with this side. Hiccups. So what is the reason for that? And we did this before. Whenever you're working with something and its complement and getting a conclusion, that's easy. That's the complement law. Are we done? Well, almost. I have nothing unioning thing. Nothing unioning thing would give me
Thing.
thing. By the way, I no longer need parentheses, and I really don't want parentheses. If I have parentheses, it gives me the feeling that I'm not quite finished. This is by what law?
Identity.
Identity law. Good. We didn't do anything clever. By identity law. Okay. Before we continue, any question on this? Is this pretty straightforward? This is a game. There really isn't a whole lot of there's not a whole lot of creativity. And I'm going to make an assumption here. I'm going to assume all of you guys are going to take a higher level proof-oriented class at some point in your lives. It's not unreasonable because a lot of you will take an upper division version of this class, let's say, or an upper division version of linear algebra. And you can have to write proofs that are, a little more strenuous than this and a little longer. But the nice thing about proofs is when you're writing a proof, especially if it's something fairly big, there is no one size fits all. If you accomplished your goal, then your proof is good. But the words you use, the order you do things, your ultimate goals within the problem can be very, very different. So we say some proofs, we call them brute force. They're just, it's not very nice, but I got the job done. And then other proofs we say are elegant because they're worded so well and it's so clear and it's just, sometimes it's clever. But when you're writing a proof, you actually have license any way that's legal to get there. Right now, there's no need to write an elegant proof. This is not a brute force proof, but this is a proof where every step was kind of automatic, right? The only time I had a choice is if I wanted to use the double negative and take an extra step. The one thing you cannot do though, I cannot go from here to here and then quote two laws. That is an absolute no-no. That would be like doing an algebra problem and simultaneously, distributing something and then taking a root while I'm raising the quantity to a power. No, these are completely unrelated separate steps. They have to be done one at a time. You can't do multiple steps at one time and then give me all the reasons at one time. Nah, that's totally fudging it. So we don't want to do that one. Now, this is pretty straightforward.
I have a question.
Yes. Now that I'm
Would you recommend also to draw a picture to see what we
yeah.
correct?
Yeah, I will do that right now. In fact, I'm glad you asked. So it was A minus B. My lighting is really not good here. That's why I have to strain sometimes. You never have to draw a picture. You're doing this on your own. You got this answer. You feel pretty good. You should. There's no place you can see an obvious error. But just like in algebra, is it possible I could inadvertently switch some of my unions and intersections? Is that possible? Yeah, especially when I'm applying Demorgans law. That's the number one place it typically happens. So at the end of the problem, okay, there's B. At the end of the problem, this is what I would do just because the problem's not that complicated. All right, what is A minus B? What is A minus B?
The A without B.
So it's this part here. Agreed? That's A minus B. Now, the first part says I have all of A, and now I want to remove A minus B. What does that leave me with? Do you agree it would just leave me with that? If I take all of A and I remove the orange, is that what I'm left with?
Yes.
Is
And
that
this-
an answer?
Mhm.
Rejoicing, confetti going everywhere in the streets, right? Dancing like the end of World War II, right? The whole, kissing the nurse thing. Yeah, but I strongly suggest things like this if you aren't absolutely certain of your steps. This one here, pretty straightforward. Not that likely you made a boo-boo, but now I'm pretty sure I did it right. Now I'm going to introduce a completely different form of the same type of problem. And this is actually referred to, what we're going to do next is actually called Boolean algebra. Some of you have heard that term before. Boolean algebra is named after George Boole, who was a mathematician, lived a long time ago. He created a lot of the logic that we use actually in computer science. He was way ahead of his time. There were no computers yet. So Boolean algebra is almost identical to what we're doing, but we invent an entire new set of symbols. I think somebody was just really bored and they said, let's reinvent how we do mathematics. It's just one of these funny things. I'm not sure why. And we do things like this throughout mathematics. We'll say, well, I'm going to define a new meaning for something. And you can do this as long as there's a consistency within. So let me show you what we're going to do in terms of analogies. So what we were doing, let's consider we have A union B. We could have A intersect B. We could have a complement. I could have the entire universe. I could have the empty set. These are the types of symbols we just did, not the operations, the symbols. In the Boolean algebra, we don't use A and B as sets. We use things technically as variables. So we will call them A and B. So here we have, I'll try big A, comma B. Here we're going to have little a, comma little b. So the analogy of this step here, the analogy of the union is we're going to say A plus B. Whoa. If the union is A added to B, anybody want to guess what they think the intersection would be? Just
A minus B.
no. Think
A times B.
A times B. And we actually use the dot. We don't write AB, we write A dot B because it's the actual symbol is important. So from a notation standpoint, when I was doing the union of sets, I am adding A and B. When I'm doing the intersection of sets, I'm multiplying A and B. And when I'm doing the complement of A, we use a bar in this case. Now that's not completely, out in left field, because in statistics, we often use a bar for complement. So that one's not really too weird. Now the next two are totally weird. If I consider my universe the whole, everything, then the universe is indicated by the number 1. Whoa. Then what do you think the empty set would be?
0.
0. And so here's the analogy. This is clear in every textbook, but it's not often obvious that we just did all of the algebra with statements of this form. We're now going to do the same thing with statements of this form. This is called the Boolean algebra. And this is actually, people will use this in programming. As long as I understand the analogies, it's not that complicated. So let's do a problem again from beginning to end so that we can see what it looks like and what's legal and what's not legal, that kind of thing. It's definitely not difficult though. It's just different. All right, so problem I want to do is A plus B dot A. So I want to manipulate this and simplify this down to the end using things like commutativity, distributive property, Demorgans if I have to, all of the different same rules, and the rules actually will look similar. So this is equivalent to what? This is equivalent to, if I use the other notation, A union B. What do you think?
Intersecting A.
Intersect A. That would be sort of the equivalent problem. And I don't want you to translate. I don't want you to rewrite it, but I just want you to, if you get stuck and say, I'm not sure what I should do next, well, what would you do in that case? So the first thing I want to do is clearly, I want to be able to do the distributive. But to do the distributive, I need the A over here, don't I? Everybody got that? I would need this to be in the form, because that's how we define the distributive. We distribute into. Okay, so my first step here is that, and by the way, here we would use 1, 2, 3 bars, but we're treating this more like an algebra statement. So we will actually use an equal sign. Again, I know rules and regulations, that is not something that's a deal breaker, but just understand from a notation standpoint, we're saying mathematically that statement is equivalent to that statement mathematically, because these aren't numerical values. We're treating these really like algebraic statements. So we're going to say this is equal to A times A plus B. Now, what rule did we just use? Anybody? All right.
Associative.
When you go back and forth to work, that's called.
Associative, right?
When you go back and forth to work, that's called. When you drive back and forth, that's called.
Commutative.
Oh,
Commuting. That's what commute means. Back and forth, literally. Oh, associative, by the way, just to remember, if I asked you, I want you to add a bunch of numbers together. It could be 3, it could be 3,000. I want you to add a bunch of numbers. You say, well, I want to add the first 2 and then take that result and add it to the third. Or I want to add the second and third, and then I want to add the first 2 that result. Well, we know we get the same thing.
Can I ask a question, please?
Oh, right.
Professor, now I'm confused.
Say again?
I'm really confused because I'm I'm looking at the book right now, and they use like where you have unions and intersection of sets. The book is put in the regular equal sign, not the 3 lines.
Oh, okay. Yeah, usually it's because it's called set equivalence, because that's actually what the title is. Remember, I said that's not a deal breaker. Don't sweat that. It's just really here that we typically will use an equal sign. Now, you notice in this, I didn't rearrange. Associativity is regrouping. And by the way, I taught remedial algebra for years. How do you get people to remember? Well, it's commute. It's easy. Commute. You go back and forth when you commute. Oh, so A plus B, B plus A times B, B times A. I'm commuting the symbols. I say, when you're at work, you're working with your associates and you're getting the job done, and it doesn't matter how you form your groups. You have all the same associates. How you form your groups doesn't change anything. I know that's kind of a stretch. So the idea, associative law, is when you regroup things, but nothing moved. Because this says I'm going to do these first and take the result, add it to here. This says I'm going to do these first and then take that and add it to this, which means I did things differently, but I got the same result. you don't have a lot. You're just not going to see associative property. It's there. You're just not going to see it used a lot, but you will see commutativity used because commutativity will always be a precursor of the distributive property. Because the way we define distributing, we only defined it on the left. We didn't define it on the right. That's actually important. Oh, okay, I got it. We have left distributing only, so that's why this is here. So let me put down the rule. This was commutative. That's the commutative property. All right. Now, if this was a multiplication, you'd say, yeah, I want to multiply into this. So if I was multiplying into this, what would I see? Well, over here, let me do it over here. What would I see? I'd say A intersect A, oops, A intersect A union A intersect B. Agreed? Everybody agree that's what we have over here?
Yep.
So what would I have here?
A plus A B.
A dot A
Right.
plus A dot B. Now, I'm doing this just to illustrate how similar they are. I'm never going to ask you to do this while you're doing this. Is it a bad idea to do this maybe on a separate piece of paper? No, it's just overkill once you get the hang of it. So what did we just do? In both cases, what did we do? Think algebra.
Distributed.
We did the distributive property, yeah. Okay, now that's where it gets a little bit tricky. A intersect A.
Isn't that a squared?
A intersect A. Let's start with this guy. A intersect A is
A.
A. But why is A intersect A A? When I combine A with A, and by the way, it'd be the same if I said A union A is A. When I combine something with itself, you said squared, it's kind of like that. This is the analogy I gave you that we actually use in linear algebra also. When a matrix equals the square of the same matrix, and I have A intersect A, this is one of those rare ones. Anybody want to try this one?
The idempotent.
This is idempotent, which is kind of a cool word. It's idempotent. So, by the way, someone said A squared. The problem is we only have add and times. We don't have exponents. So exponent isn't an operation. Oh, but if I had said A intersect A intersect A intersect A intersect A, do it 25 times, it's still A. So A times A times A times A times A is still A. Does that make sense? Because the times is treated like the intersection is over here. And that's one that's not obvious. So A times A is A, and that's idempotent. Now, I would really like to be able to combine these guys. I would really like to be able to combine these guys. Well, over here, what have I got? Over here, I've got A union A intersect A union B. I know that. And you say, well, am I just going around in circles? No, because I'm going to be able to end up with just one thing really, really soon. We know this is true. And again, that's the distributive property. The problem is I can't do that yet. I'm not there yet because don't I need, if I said factor, or let me do this. This is algebra. This is regular old everyday algebra. AB plus AC. Okay, everybody's cool with that? If I said I've got A plus AC and I want you to factor it, would anybody be challenged by the factoring of this? But I don't have a B there. No, what do I have there?
One.
I have one. Oh, so here's what we have to do. We have to create. We're going to say this is A times 1 plus A times B. That gives me the, see, I can't factor this out because there's nothing, I actually have to have something there in the set Boolean algebra world. So I'm going to create the 1. So think backwards. A times 1 is A. This is the equivalent of saying over here, A intersect the union is A. That's the same thing. Okay, what rule is A intersect the union A? We've done this.
Like identity law.
That's the identity law. Exactly. That's an identity law. Things involving union and empty set usually are identity law. So this is identity law. So I actually had to do this before I can get to there. So it's identity first. This required one extra step before I could get something like that. Now I can use the distributive law. Remember, in algebra, factoring is the distributive law, just in reverse. So can I write this now? Is that legal?
Yep.
Yeah, that's now it looks like, let's see. Oh, we're almost, let me go put this one now. This is now the universe intersect A intersect B. Okay, over here, I have, what is 1 plus B? Things are a little bit out of order now because I had to do this step. What is 1 plus B? That's kind of like saying the universe or B. What is 1 plus B?
One.
I have the universe or I have B. I have the universe or I have B. What do you think?
The universe.
If I have the universe or I have B, I think I have the universe. Now, this makes it easy. I just kind of gave it away. I have the universe or I have B. We agree they have the universe. What kind of rule would end up with that? Well, which rule has the word universe in it?
Universal bound.
That's the universal bound. Yeah. I'm trying to make it easier. Go, oh, okay. Now, A. What is the times? That's intersect. Now I have A or intersect, if you want to think of it that way. A intersect everything. A intersect everything is just A. And again, that's back to the identity law. Wow. So this ends up being this. It's never about the result. That's irrelevant. It's the path and the reasoning. And this really mirrors. You're going to find you don't have to do very many of these. And in the textbook, it's really, really laid out well. It's really easy. In the big picture, this is just a thing. This stuff here, I think, is way more important in the big picture. Okay, because this is used in so many different areas mathematically. This is very specific. Okay, we're doing this right now. We're never coming back to this one. This one here, you're going to see in other capacities mathematically and in other classes. So if you said, well, which one is more important? Well, no, that one's more important, but this is an analogy of that, which is how you're probably going to be able to remember it fairly simple. Okay,
Professor,
so yes.
could you go back to those last two steps on the right side? For some reason, it's not clicking.
Well, the right side deviated because I had to do stuff over here. But right now, hold on a sec. I may have boo-booed over here. Hold on a minute. A intersect A union.
Just the
Intersect
last two steps.
A union A. Intersect A union B. Hold on a second. There's something they're not quite going to get the same thing here, are we? Hold on. I'm not liking something here. A intersect A union B. So A intersect A union A intersect B.
You had flipped the A union B and A intersect B for the bottom two. I'm just not sure how that happened.
Hold on. Oh, you're right. Yeah, I hold on. Yeah, you're right. That's A union A intersect A union B. That's correct. Hold on.
So there should be.
There's a boo-boo here somewhere. Where is it? This is correct.
And then the next one will be distributive.
A union A intersect A union B. What did it? I wrote universe, didn't I? Oh,
Yes, and it's just A, right?
yeah.
Okay, all right.
It would be
we're
so
back.
great if Tom union Tom was the universe. No, Tom union Tom is Tom. Yeah, sorry, that.
I'd like to differ, but it's okay.
Oh, I'm glad you guys caught that. Yeah, I'm looking at it going, that's not gonna work. Now that's gonna be what? A. Now, this is a little bit different because of the order change, because I had to add that stuff. I can stop here. I don't need to do the distributing. A intersect, that union is just A. This is one of those obscure ones too. Does anybody know what that one is?
We've done this in class before.
This one's a little bit vague.
It's the absorption law.
That's the absorption law.
I had something to say about this one because if you go to the very top, it's actually the same.
Yes, but the absorption law, it's basically, again, the way it's listed is usually because some is an ordering of things. Now, from a picture standpoint, this one's really easy. You can't do this one from a picture standpoint, unfortunately, unless, okay, it's kind of cheating, but you know what? I'm trying to justify my answer. We did this whole problem, regardless of how you did it, you did the whole problem and you got A at the end. But from a picture standpoint, let me do this from a picture standpoint, okay? Again, this doesn't give you the answer. This is to help you convince yourself that what you did was correct. That's the only reason you would ever do this. You do this after the fact, not before the fact. So A union B, let me use orange because orange isn't as loud. A union B is all of that. I want, where does A union B intersect A only? Well, A only. If we agree that this is equivalent of A union B intersect A, then shouldn't we expect our final answer to be of this form? That's my point. Now, I can't make it be this. If I make a mistake along the way, it's not going to work. But to convince yourself, yeah, if you had just simply moved that in front, you could have used absorption, but we went through the process. Why? Because I wanted it to match what we did here. That's why. Not because, oh, we could have been lazy and just did it. Well, but we weren't doing this problem. We were doing this problem. So I was trying to show you the analogies. There's no absorptions here. This is, I actually have to do these steps. But the thing is I don't think anybody should be challenged by the Boolean algebra. You know, things like, oh, let me throw one at you then, because there is one that I did not go over in the Boolean algebra, and it's probably the most important one. Clear, I've tried to make this clear. What do, at least according to Mr. Brown, what is the most important of all the laws that we've used so far, by far?
Demorgans.
Yeah, this is not even close. I mean, that's the one that gets used the most, and that's the one that is the most treacherous if I make a mistake. So the two versions of Demorgans law, these are the two versions. And I want to give you the Boolean algebra analogies to both of them. That's why I don't want to forget that. I would be remiss if I left that out. So we know this is equivalent to A complement intersect B complement. We know this is equivalent to A complement union B complement. Okay. A plus B. How do I indicate complement? Do you remember the notation I introduced? How do I indicate the complement? Which symbol was complement for the Boolean algebra?
Line above.
A bar above, and it would be a bar above the whole thing. This would be the analogy. So what does this equal? A bar and B bar
With the
what
times.
operation? With the times. Perfect. Now, do you see the clear analogy then? Does everyone see the absolute analogy right here? This is Demorgans law applied to the Boolean algebra. Now let's do it for this one. A times B bar, A bar, B bar, clearly, plus. So this is Demorgans law for the Boolean algebra, and it, oh, absolutely, it will come up. What do you think this is?
Just A.
Yeah, because the complement of the complement. Now, if that statement came up, which by the way, it will, now I can say double complement. Okay, because why is this true? Because I'm actually physically doing a double complement. There's no problem with that. Okay, that is a double complement if that came up. Oh, again, that's not. I was like, I never didn't do that thing. You know, hopefully you don't have people talking like that, trying to figure out, okay, hold on, say it again, because I got to put my negatives in there and they all canceled and so on. All right, we're at a good place. This is exactly how far I wanted to get. So let me go ahead and pause.